You found the skeleton. How would you tell it's a dinosaur? You personally, how would you decide?
Well, interesting question. I don't know. I'd have to do some research on that.
Hey there YouTube, the Dapper Dinosaur here for a rare part 5 to a series. Normally I like to keep it to 4, but that would have made this part like an hour and a half long on its own or something. When last we left off, Pam was lying about ENCODE and their findings, but now I guess we're on to more stuff about how really the genome is totally functional, you guys.
There are other elements of the genome that are thought to be junk, and one candidate was pseudogenes. So pseudo means sort of, right, basically. And pseudogenes share similarities in sequence to regular genes, but they're slightly different and they don't function as genes.
I'm really looking forward to what use a broken vitamin C gene is to humans and other monkeys that share the mutation that broke it.
So they're called pseudogenes, and they were thought to be evolutionary leftovers, sort of like vestigial organs for your genome.
They're still known to be that.
Because they got copied at some point, and so then you had two copies of a gene, so one copy mutated, and it just kind of kept mutating, and it didn't really matter because it wasn't being used for anything. So it could So this is thought to be evidence that some of the genome is junk.
Nope. There's no need that the gene be duplicated, just that it break. It's not like humans have a functional vitamin C synthesis gene and another broken one. If they did, then humans wouldn't be susceptible to scurvy, but they famously are. That being said, a duplicate gene certainly can become a pseudogene. For example, humans have a bunch of copies of the amylase gene, which helps humans digest starchy food like grains and potatoes. If one breaks and no longer produces amylase, it'll be a pseudogene.
But it turns out that pseudogenes are often playing critical roles in the regulation of the genes that they resemble.
By often, she means rarely, and there's no particular correlation between neo-functionalized pseudogenes' original function and their new function. Sometimes there is, like elephants using a pseudogene that originally helped prevent leukemia as a regulatory site that causes apoptosis in precancerous cells to suppress tumor formation, but that's not because it's directly regulating a functional version of the pseudogene. Generally, this actually relies less on the pseudogene directly and more on its own regulatory region, which is co-opted to regulate another gene. Pseudogenes often lack regulatory apparatus altogether, making neo-functionalization as a new regulatory element nearly impossible.
So the way that they're expressed in RNA actually determines the way that the genes are expressed in the cell, and this can be important in either turning the gene on or turning the gene off.
Yeah, sometimes it is, but it's not always. And further, we can check to see if a pseudogene is under purifying selection. That is to see if it's sequence constrained, because if it has been neo-functionalized to act as a regulatory region, then it will be under selection pressure, and we can see lower diversity in that region of the genome than would be expected given the background mutation rate in the genome as a whole. Now, what do you know, but we find most pseudogenes accumulate mutations at a rate consistent with not being under selection, meaning that they cannot have any function that is sequence dependent, meaning they're not regulating anything.
And gene regulation is a hugely important concept. It's very, very difficult to wrap your mind around, but basically you have the same information in every cell in your body, but your cells are all very different. So your eye cell is different from your liver cell, and they're different because certain genes get expressed and other genes don't.
That's true.
Right, so this whole process of gene expression is what enables you to be a multicellular organism that has different organ systems, and you have eyes that are transparent so that light can pass through them, and a skin that is not, so we can't see your insides, which we're all very grateful for.
It takes a lot more than that. For example, sponges have different cell types, which requires gene regulation of the type Pam is discussing, but they don't even have tissues, let alone organs. That being said, you do need cell type differentiation to get organisms and tissues, so it's more that she's leaving a lot out, not that what she's saying isn't true.
Okay. So this is, it's complicated, and I apologize for that, but it's hugely important. So what they're finding basically is that all these regions that were thought to be junk are actually not junk, but they're involved in this. Am I off?
No, in fact, they're finding that some regions are functional, and we have a test for that. We just check to see if they're under selection. It's really simple. When we find an area that's under selection, that demonstrates that it's doing something even if we don't know what. And if it's not under selection, then it's not doing anything, because it doesn't matter what mutations occur to it. I'm going to cut out Pam's fumbling about with technical problems. They seem to only be real in her head.
All of these regions that were thought to be junk are involved in this very fine-tuned dance of what protein gets turned on when and where so that you can be a multicellular organism. So it's not junk, it's actually useful.
This is a hellbender. Hellbenders are salamanders. The hellbender adult is between 30 and 74 centimeters long. Therefore, all salamander adults are between 30 and 74 centimeters long. Can anyone see the problem with this? Virtually no salamanders apart from hellbenders are even close to that big. Hellbenders are exceptional, and in no way should be taken as representative of salamanders as a whole, even though they shouldn't be ignored. Similarly, the fact that in some parts of the genome, that in most organisms don't have function, we can find some function in some organisms, doesn't mean we get to simply declare that that entire class of genome regions are broadly functional, especially since we can check for function. This is just Pam affirming the consequent. If A then B, B therefore A, is fallacious. Here, A is the genome is virtually 100% functional. Therefore, her B, some pseudogenes will be found to have function. That's a reasonable possibility. If A is true, B follows. But then she uses the fact that B has been found to be correct in some cases, that some pseudogenes are functional, to then demonstrate A. That's not how this works.
This is a problem for evolutionary theory.
No, Pam being logically fallacious and also being factually wrong is not a problem for the theory of evolution.
And a score, if you will, for genetic entropy.
No, the fact that there exist neo-functionalized pseudogenes means absolutely nothing for genetic entropy. Even if Pam were right, it wouldn't help genetic entropy one bit.
Okay, second problem is harmless mutations.
It was at this point that Dapper decided to go get a tall glass of whiskey, because there was no way he was prepared for whatever stupid shit Pam was about to say.
Now, if I texted you this, you would understand what I meant, right?
Nah, I'm way too into apophatic theology for that silliness. Get out of here with that saying what God is like. We can only say what he's not like, because what he is like is so far outside the realm of human or dinosaur experience that any positive attribution of a trait to God is automatically going to be wrong.
And you might text back something like all the time if you were involved in Steubenville retreats in the late 90s or early 2000s. Right? If I texted you would say, well, Pam Acker really needs to proofread her text before she hits send, but I still understand what she's saying. If I text you this, now you think I am telling you that whatever you just said I understand, but I'm using very poor grammar.
No, I actually think that you're telling me that your life is currently going well, because I will understand that to mean that you have dropped the first-person subject, which is fairly common in very informal English. Do it myself all the time. If there had been a comma after it, then I would have taken it as Pam is indicating here.
Right, and the original message is completely lost. But each of those individual mutations, so God, it good, or got is good, you probably would be able to get the original message from that, God is good, right? But when I put them together, I've completely altered the message.
Hey, if you're filling out a bingo card and you have "and your point is" in there, feel free to mark that square.
So this is a very simplistic example because it's only a few letters long and your DNA is 3 billion base pairs.
And also isn't English and doesn't function anything like any human language.
But it illustrates something very important, which is I can have something that is quote-unquote harmless or neutral, but as I add together those harmless or neutral mutations, I end up with a very deleterious effect. I end up losing the original message.
So let's figure out the analogy, stupid though it may be. Basically, the text messages are supposed to map onto DNA sequences that are functional. The first change is neutral in that while it's a bit harder to figure out the message, it still works to convey the intended meaning. But then the second one changes the meaning altogether. DNA sequences aren't hard to parse for the cell, and if a mutation changes the function of a region of the genome, it's not likely to be neutral. This is why analogies between human language and how genetics works are almost always a bad idea. In fact, I'm just generally not a big fan of analogies for genetics at all, because they tend to always lead people into sloppy and erroneous thinking.
And that's actually what happens in organisms as well. And it's a big problem for organisms because natural selection, which we talked about in the last presentation, it only works on the level of the phenotype. This is the physical expression of the genes. So I might have a mutation in one of my genes that makes it work just a little bit less effectively than my neighbor. But
then it's not likely to be neutral. If it is, then that function wasn't important. An example is the aforementioned loss of the ability of most primates to make vitamin C. The primate diet is universally rich in things like leaves and fruit, which generally have more than enough vitamin C for the animals to survive. Indeed, even in humans, scurvy is very unusual except in cases where access to fresh vegetables is more or less impossible, like on a long sea voyage in the Age of Sail. So when the gene broke, it went unnoticed by selection because it didn't actually affect the ability of the organism to reproduce, and it generally still doesn't in primates today. So it was a neutral change, and if it doesn't affect fitness, then it's not genetic entropy, because genetic entropy is about declining fitness. The reason such neutral loss of functions are talked about in regards to genetic entropy is because its proponents unilaterally redefine fitness into some nebulous concept about how well-functioning the organism is by whatever arbitrary metrics they find significant. But that's more or less the same as a flat earther deciding that they can explain what the globe heads call gravity by saying it's actually electromagnetism, which requires a redefinition of electromagnetism because otherwise the gravitational acceleration we measure wouldn't correspond to electromagnetism. Creationists really aren't any better than flat earthers, they're just more popular, well-funded, and slightly better at hiding their absurdities in areas that the general public won't notice.
At the level of phenotype, that doesn't really come through. It's not like I'm missing a leg, it's not like I can't run away from predators, it's not like I can't, eat or something like that, so I survive.
Evolution isn't just about survival or not, it's about differential reproductive success. If your mutation means that you have fewer offspring than average, it's being selected against. And if it's not, then it's not harmful.
And I pass along that slightly damaged protein to my offspring. And I might even have more offspring than my neighbor.
Then it's not a harmful phenotype. At least not if those with it consistently have more offspring. See what I mean about redefining fitness?
And so what happens over time is that slightly damaged protein becomes more and more prevalent in the population. And my offspring add their own mutations, which damages it just a little bit more, or damages another part of their genome a little bit more. And what gradually happens over time is these small changes that are not harmless or not harmful at the level of the phenotype in themselves, they accumulate over time and translate into something that is ultimately very harmful.
And when that happens, the mutation that finally makes the phenotype less fit can be selected against. All Pam is saying is, what if there's a bunch of neutral mutations followed by a harmful one? And the answer is, then selection will act against the harmful one. And it's not like the whole population is likely to get the harmful mutation all at the same time unless it's severely inbred, which by definition leads to lower genetic diversity, which is the opposite of what genetic entropy says is a problem. Basically, this argument boils down to, if we just pretend that evolution doesn't work the way it works, then it might be a problem. Which, yeah. Fortunately, though, evolution does work the way it works. So we don't have a problem here.
And so, sometimes people twitch when I put up this graph because it's not super easy to understand. But this was published by a gentleman named Kimura.
Oh good, we're going to get Pam repeating Sanford's lies about Moto Kimura's work on neutral theory. This ought to be fun.
In the 80s, I believe, and he was looking at, he was trying to define these neutral mutations, and he was saying, most mutations are negative. You can't even see positive mutations on this graph, by the way.
Yeah, that's specifically because he excluded them from consideration, not because they're so rare, but because if he let in any amount, then positive selection would swamp his models, and he could no longer recover any data about neutral variation, which was the whole thing he was looking at. Then along comes Sanford and just straight up lies and saying that actually he didn't include beneficial mutations in his math because they were so vanishingly rare. Now here's Pam swallowing this bit out of Sanford.
There are so few of them that you can't even see them. Most of them are negative.
Yep, that's the lie Sanford told. And look, if you want to tell me that the inventor of the gene gun isn't lying, then that's great. I look forward to your evidence that he's just so stupid he can't understand the most basic aspects of Moto Kimura's work. Because he's either incredibly stupid or he's a liar. Take your pick, creationists.
But most mutations, they're only very slightly negative and they fall in what he called a no selection zone.
Uh-oh, that's not true, is it? The size of the selection zone is not some fixed thing, and in fact, the size listed from minus 0.05 to 0.5 by Sanford's butchering of Kimura's graph would only apply to a species on the brink of extinction. This might not be immediately obvious, so let's dig into this. Genetic drift is an important aspect of evolution that is often overlooked in favor of the admittedly sexier idea of selection, whether natural, artificial, or sexual. While selection is non-random, drift encompasses the random aspects of the variation in allele frequency in populations other than mutation. Suppose you have a neutral mutation. Suppose you have a codon in a gene that says TTA instead of the TTG that is in your parents and everyone else. That means that it is a new variant in the genotype. But both of these codons code for the same amino acid, leucine. That makes this, near as we can tell, a truly neutral mutation. The amino acid sequence of the protein the gene codes for isn't even changed. So will that variation that you carry spread through the population or go extinct? There's no way to say for sure, but the chances are proportional to how common it is. In this case, very much uncommon. And inversely proportional to the population size, because it needs to spread through that population. One of the things this means is that the larger the population is, the harder it is for an allele to randomly reach fixation, and provided it is already at a wide distribution, the harder it is for it to randomly go extinct. Now, it should be noted that the population size we are concerned with here is effective population, and that is not strictly the same as just the number of individuals alive in the population at a particular moment. It is affected by things like genetic variability already in the population, as well as population structure, which makes mating non-random. However, generally speaking, the larger the population is in terms of just individuals alive in the population, the larger its effective population size is. What this means is that not only is Sanford wrong about the distribution of mutations, not only is he wrong about mutations having fixed versus contingent fitness effects, he's also wrong in assuming that there's some single no-selection zone. Now, it's true that any population of finite size will have variations that have negative fitness effect but cannot be selected against, because the strength of the selection is too weak. But this is a problem specifically for organisms with small populations and low genetic diversity, which is the opposite of what Sanford is arguing. And of course, this is just Pam parroting Sanford's claims, so I'll criticize Sanford. This problem with low selection strength and high genetic drift strength occurs specifically in these small populations, and so the outcome is that the less genetic diversity there is, the worse for a species. On the other hand, Sanford's whole point is that the more genetic diversity increases for mutation, the worse off a species is. But that's obviously wrong for the simple reason that more genetic diversity increases effective population size, thereby reducing the strength of genetic drift and increasing the ability of selection to act. Basically, Sanford's ideas are wrong at essentially every turn. If you'd like more information about this, I'd encourage you to watch the stream I did with Dr. Zach B. Hancock, a population geneticist, or if you'd rather have it straight from the ape's mouth, this video by Dr. Hancock that is a book review of Sanford's work, Genetic Entropy and the Mystery of the Genome.
So natural selection cannot eliminate these negatives from the population. It can only eliminate really negative stuff from the population that makes your fitness level go way, way down.
That's not really true, though. These fitness levels are a measure of how much more or less than average an organism will produce offspring who themselves reproduce. So the average would be 0 by definition. A fitness effect of 0.002 would mean that on average an organism with that allele would manage to produce 0.2% more offspring that reproduce than the average member of the species. As you can see, that's a fairly minor effect, and it's within the no-selection zone given by Sanford and copied by Pam. But what's the actual no-selection zone for humans? Well, assuming a conservative population size of 7 billion individuals, the human no-selection zone is more like 0.00000000002 to 0.000000002. And that's rounding to make it bigger than it really is. That means that in humans, a mutation that causes an average increase of just 0.001% in reproductive output will be heavily selected for, and one that causes the same level of decrease in population output will be heavily selected against. As a result, it's simply not true that one can declare that most mutations are within the no-selection zone. That has to be measured in a case-by-case basis, and in many cases, it's simply not true.
It cannot eliminate these slightly deleterious mutations, and slightly deleterious is not the same as not deleterious, right? So evolutionists who argue that most mutations have no effect because they're quote-unquote neutral are really pretty guilty of sleight of hand.
No, that would be creationists who are lying about the difference between neutral mutations, which is most of them, and deleterious but unselectable mutations. Rounding to 1/10, about 90% of the genome is non-functional and not sequence constrained. That means about 90% of mutations occur in places where it doesn't matter in the least. Now, beneficial or deleterious mutations in these regions aren't impossible, but it's very hard to do because it requires things like reactivating broken genes, which is easier said than done with mutations. I also gave the example earlier of a mutation between synonymous codons. These are generally neutral as well. This means that for most mutation, the actual fitness effect is literally 0. It makes no sense to say that selection would act on a mutation with 0 fitness effect. Kimura's distribution actually reaches the highest value at 0, meaning again that that's the most common kind of mutation according to the source that Sanford and now Pam are butchering. Mutations are said to be neutral, beneficial, or deleterious exactly based on their fitness effect. Neutral mutations have a fitness effect of 0. Beneficial mutations have a positive fitness effect, and deleterious mutations have a negative fitness effect.
Because if it's slightly deleterious, that doesn't mean it's neutral.
Correct, and I'm not aware of a population geneticist saying otherwise.
And if I accumulate slightly deleterious mutations over time, I end up with something really deleterious.
But you see, you can't, and it's actually not hard to see why. Now, in the real world, a mutation's fitness effects don't combine in a mathematically simple way. For example, there could be 2 deleterious mutations that when found together are actually beneficial. For instance, maybe each produces some protein that does nothing but get in the way of cellular processes, but when both are present, they interact to enhance some cellular process. But for the sake of simplicity, let's say that we have an organism with an accumulation of various deleterious mutations, and then it has offspring with another one that, now presents a real problem. Well, it means that the fitness effect of this new mutation, while on its own might be small, it is now not so small. This has caused a significant decrease in the reproductive output. But notice what it also does. It takes it away from the no selection zone. This means that this mutation, which on its own might have been subject to drift, is now subject to selection. And this is because fundamentally selection is done on an organismal basis. And fitness is a measure of the whole organism's reproductive output, and genes only modify it. So it might be that an organism whose fitness is 99.9998% that of the average may not be selected against because of the strength of genetic drift, but that at 99.9997%, it and those like it are selected against. That can be all it takes. So the accumulation of these mutations will reach an equilibrium so that in the long run, those that take organisms outside this no selection zone will be selected against.
Right. I end up eventually with, not just a disapproving giraffe, but I end up eventually with error catastrophe in my genome. I am no longer going to be viable as an organism if I accumulate enough of these slightly deleterious mutations.
Yes, error catastrophe is a real thing, and it has been seen in viruses. But here's the thing, we can calculate the maximum mutation rate for an organism to be able to persist at a particular rate of reproduction. I won't go into all the math, but think about this. If a fruit fly lays 500 eggs in its life, or fertilizes the same, which is a pretty normal amount, how many of them have to survive on average to reproduce for the species to stay at a steady population? Ultimately, only 2. This means that even if only 0.4% of the offspring on average survive to reproduce, fruit flies are good. Now, the higher the mutation rate, then on average, the fewer offspring on average will reproduce. This means that all organisms have to reproduce above the theoretical minimum replacement rate in order to get the actual theoretical replacement rate of 2 per pair for organisms like humans with male and female members. The higher the mutation rate, the larger the number of offspring needed to hit that replacement rate. Well, I'm not going to go through all the math for it. See Zach Hancock's video I recommended for that. But when you actually do run the math, you find that virtually every organism has a mutation rate well below the level needed for them to persist indefinitely. That this is the case should be obvious simply by the fact that organisms are around. If the population had a mutation rate high enough to cause error catastrophe, it wouldn't persist long. For humans, the number of offspring needed to account for the human mutation rate is about 2.4 per female. Historically, this is well below the average human fertility rate, although the world fertility rate as it stands seems to be at 2.3, which means in fact that we may be starting to see some population decline in humans in the coming years. Something which is possible based on the trend in population growth. However, it's also the case that 2.4 is a high estimate, and empirically determined estimates from numerous sources, including the United States Census Bureau, put that number at 2.1. So we probably have decades before the human population starts to decline or stabilize.
Not to give you a spoiler or anything, but that is where we're headed, is error catastrophe.
Yeah, if the birth rate in places like the United States stays at the low 1.64 it's currently at, and that low birth rate spreads, but humans are known to artificially lower their reproductive output by choice. Not many organisms do that, so while error catastrophe could be a problem in the long run for humans, with this rather odd tendency, it's not a problem for basically any other organism except those with blisteringly high mutation rates and small genomes, like viruses, who like to operate right on the edge of error catastrophe. Also, I should point out that if the tendency to not reproduce at or above replacement rate in humans is itself heritable, then natural selection will fix that problem in short order because the people who tend to reproduce at or above the replacement rate will quickly be selected for.
Okay, problem number 3. Are there good mutations? So when you think of mutation, what do you think of?
Something in the genome that was not inherited from one's ancestors.
Yeah, Godzilla, that's a great mutation.
I mean, yeah, I'm a big fan of Godzilla. I even did a show about Godzilla with Aaron Ra and Paul from Paulogia. But unless I'm talking about fiction, that's not what I think of when I think about mutations.
All right, I normally think of cancer.
Dark, but okay. Cancer is caused by mutations in cells that cause them to keep reproducing when they ought not to.
You might also think of other genes. So This slide is particularly poignant to me because those are my grandparents who both died of cancer.
Hey, that sucks. Cancer sucks, and there's nothing to sugarcoat here. While mutations are the source of new genetic material, there's also no denying that they are the cause of immense suffering in various individuals. I'm not here to downplay that, and I'm sorry for Pam's loss. I recently lost an uncle after a years-long battle with cancer. A good friend of mine lost his father to cancer a few years back. But that tragedy and suffering does nothing to change the fact that beneficial mutations are observed in the wild and in the laboratory.
And below is my niece, who has been diagnosed with type 1 diabetes, as no one else in our family has it, so it's a novel mutation in her.
Probably, although not certainly. And yeah, that sucks. A childhood friend of mine passed away in his 30s because of type 1 diabetes. But again, this doesn't change anything about the fact that there are beneficial mutations. This is like me trying to argue that the offensive line of the Green Bay Packers doesn't exist by naming all the starters on the defensive line.
And she's surrounded by all of the paraphernalia month. Everything. So mutations, generally speaking, when we think about them, they're actually quite bad. They cause disease and damage and deformity.
Most of the ones that aren't neutral, which is most of them, are indeed deleterious to varying degrees. This is not some revelation that is new to genetics and evolutionary biologists. Indeed, in a population with a steady size, the rate of negative mutations must be higher than the rate of positive mutations, or the population would be increasing in size. Okay, we're skipping past the rest of her examples of mutations that are harmful because no one is disputing that they exist.
So, are there good mutations?
Yes, unequivocally so. Even Kimura said as much in the paper that Sanford butchered.
Well, obviously most of them are bad.
No, most of them are neutral, and in a population that's already reasonably well adapted to its environment, most of the rest will be bad. But a population can actually be in a position where most non-neutral mutations will end up being good. Here's a fitness landscape. The peaks represent a phenotype that has a high fitness, and the troughs represent phenotypes with low fitness. So the vertical axis is fitness, and the two horizontal axes represent phenotype. Of course, in reality, you can't graph phenotype on just two axes, but this is simplified for illustrative purposes. If a population exists in what is currently a trough, such that most new phenotypes are actually higher in fitness, then most mutations that have any effect at all will be beneficial, and this will likely lead to an adaptive radiation, which is a thing that has been documented happening many times in the history of life on Earth. However, we do say that more mutations are deleterious than beneficial, and that's generally true. It's true specifically because selection means that beneficial mutations are selected for strongly, and adaptation happens relatively quickly, and when it doesn't, it usually means extinction. As a result, most populations are well adapted for their current environment and are on peaks rather than troughs of the fitness landscape. This means that any significant phenotypic variation is likely to lead to lower fitness in most populations. I want to drive home again that the fitness effect of a mutation is entirely context dependent. A mutation in one environment might be a great benefit, but in another it might be a huge problem. So in Pam's upcoming examples, remember that what's important is whether the mutation is beneficial in the environment in which the organism finds itself.
But most evolutionary biologists will put forward the idea of antibiotic resistance as a good mutation. So antibiotic resistance clearly seems to benefit the bacteria. If there's an antibiotic present, then it doesn't die. That seems like a good thing, right?
Yes, unambiguously so.
But you have to look closer than just that. Because what happens when something becomes antibiotic resistance is there's a change that happens in the bacterium itself. And so with MRSA, that change happens in the peptidoglycan that cross-links its cell wall. So normally this is a very strong linkage together. The bacterial cell wall is very stable. In MRSA, the bacterial cell wall is actually less stable. So the cross-linking doesn't work quite as well. But that also means that the antibiotic that kills the bacteria by disrupting the cross-linking, it can't bind to that peptidoglycan. And so MRSA can survive being treated with methicillin.
Hence, that's a beneficial trait in an environment with the antibiotic that it has evolved to resist, which just happens to be the environment in which it evolved, by some crazy coincidence.
But if you put MRSA in a test tube with regular Staphylococcus aureus that would die in the presence of the antibiotic, the regular Staphylococcus aureus quickly outcompetes the MRSA and the MRSA goes extinct.
Yeah, and if you put polar bears in the Sahara, they would quickly go extinct. Does this mean that Ursus martimus is inherently inferior to Canis aureus? No, obviously not. There should be no surprise that when you take an organism out of the environment it's adapted to and place it into another environment that it won't do well. This is why no humans should live in places like Russia or Canada. Humans evolved in the tropics, and those places are completely uninhabitable wastelands. Anyway, Pointing out that organisms adapt to their environment and then don't fare well when you suddenly place them in a new and very different environment is in no way a problem for evolution, because that's what evolution predicts. She just arbitrarily chose the no antibiotic environment as the default. There's no objective reason to do so. She simply does it because it's rhetorically useful to her.
Because the MRSA, in order to gain the ability to resist the antibiotic, has lost the ability to have solid cell walls that are the way that they're supposed to be. And so the normal bacteria is actually better suited to the environment when there's no antibiotic.
And the polar bear, in gaining the ability to conserve body heat, has lost the ability to rapidly shed body heat, making it spectacularly bad at living in the Sahara Desert. So what? Evolution is always about trade-offs, and adapting to one environment of necessity means being maladapted to others. Evolution isn't going to get a Superman who can survive in all environments and thrive there. It's all about costs and benefits. All benefits come with costs, and if the costs are smaller than the benefits in terms of reproductive success, then those costs are going to be paid.
And this has been repeated a number of times with different antibiotic resistances. In Klebsiella bacteria, for example, they're resistant to an antibiotic that binds to the ribosome and stops protein production, but they're resistant because the ribosome has changed shape in a way that makes it work less efficiently.
And the white fur of the polar bear will mean that any prey in the Sahara will be alerted to its presence, making hunting that much harder. Clearly, jackals are the objectively superior life form.
So if you put resistant bacteria and non-resistant bacteria together, the non-resistant bacteria will outcompete them every time. Because what's happening is it's almost like a zero-sum game, right? I can't change anything without it affecting something else.
Yes, exactly. That's the point. That's why mutations are environmentally contingent. There's no such thing as objectively better in evolution. It's all dependent on the environment, and organisms can only be more or less fit in a particular environment. Pointing out that they are less fit in an environment that they did not adapt to doesn't make them inferior or superior. Evolution has no objective criteria for bestest organism regardless of environment. Humans can come up with arbitrary criteria for that make them feel good, and they do. And interestingly, they tend to value things that make organisms more like them or more beneficial to them. But no matter what, those criteria are made up and do not affect evolution. Nor is the fact that these organisms might become subjectively worse according to some anti-vax tradcath who's appropriating both the Holocaust and art from other Christians her church has historically oppressed, something that is a problem for the theory of evolution. It's a nothing for the theory of evolution. It means as much to biology as what color curtains Pam has in her bedroom, or whether she shaves her legs or not.
So if I have a change that allows me to resist the antibiotic, it usually affects my ability to function as a normal bacterium, and it usually makes it less.
No, it makes it better in the environment to which you're adapting. That is the environment with the antibiotic. Just like adaptation to the Arctic coasts makes one less well adapted to an inland hot desert.
So it's a trade-off. It is not purely beneficial.
Yes, it is a trade, but it's also truly beneficial, because we define what is and is not beneficial based on the environment. You can't just arbitrarily decide that if you change the environment so as to make the previously beneficial mutation deleterious, this means that you've discovered there are no beneficial mutations. It just means that you don't know what a beneficial mutation is. And of course, this ignores that in many antibiotic-resistant bacteria, there are compensatory mutations that restore most or all of the function that was lost vis-a-vis the wild type.
I'm losing something, and that's called a fitness cost.
No.
I'm going to skip the nylonase as well.
Yeah, she probably should skip past the fact that a group of bacteria were able to evolve to digest nylon, a substance that was only invented in 1935. That sounds too beneficial. And of course, she let us know that this mutation was actually only a relatively small change to an existing enzyme, which is both true and irrelevant.
So there's a CCR5 delta 32 mutation in T cell that makes T cells resistant to HIV infection, which sounds like a great thing, especially if you're in a high-risk population for HIV.
Here we go. Let's hear about how in an environment with low HIV levels, this isn't good, as if that changed anything.
But the deletion also means that that protein cannot insert itself in the cell membrane. Now, it normally belongs in the cell membrane where it performs an important function in cell signaling.
Not important enough to overcome the risk of HIV in environments with high enough levels of the virus.
If it can't get in the membrane, then HIV can't attach to it and infect the cells. But it also can't perform its normal function in cell signaling, and this can lead to development of multiple sclerosis or serious liver problems.
Not according to her slide, which actually says that when it is found along with multiple sclerosis, it can cause liver problems. So the combination of traits means it's a problem. And I'm not here to say it isn't. But this just means that in HIV-rich environments, the place where a mutation like this is likely to spread, multiple sclerosis will be heavily selected against. And it will likely decrease in the population. But further, even if it did mean general loss of liver function, if that's something that would have been a problem at 50, but HIV is something that will be a problem at 20, then it remains beneficial. As I've kept saying, and as Pam has affirmed, it's a trade-off. The only difference we seem to have is that she thinks that she can arbitrarily change the environment that she would like to measure the fitness effects against to environments that the organisms are not in and so not adapting to. I, on the other hand, realize how absurd and intellectually bankrupt that is. But that's just based on what she put on her slide. We'll get more into it in a second.
So, would you rather be resistant to HIV or not have MS?
Well, that's not really a choice I have to make. In fact, I found the paper she's pretending to cite. It's increased to CCR5 delta 32/delta 32 genotype in multiple sclerosis by K. Pulkkinen et al. Published in Acta Neurologica Scandinavica in April 2004, not in Medicine as Pam's slide would indicate. I can tell because Medicine is an open access journal and doesn't have any particular article matching this topic at all, never mind from 2004, and lo and behold, they compared the outcomes of people with CCR5 delta 32 who also had MS to those who did not have MS and found bad liver health associated with those with it. It should be noted, though, that MS patients did have a higher rate of CCR5 delta 32 than the control group, and it is positively correlated with other inflammation-related diseases. It seems that the mutation does predispose someone to having inflammation disorders, but it is neither a necessary nor sufficient cause for such disorders. There are people with CCR5 delta 32 with MS and those without it. So Pam is lying to us right now. So either she read the source, knows it doesn't say what she says it does, or she didn't read it and is pretending she did. The other option is that she's too stupid to understand even the abstract. That being said, in my current environment where I'm at low risk of HIV, I'd rather not have the mutation. But that might change if I found myself in Lesotho during a condom shortage in some kind of group scene.
It's a trade-off.
Yep.
So this leads me to call this the spork problem.
You can tell this isn't a real problem in evolutionary biology simply because she's the one who named it, and she isn't publishing in evolutionary biology journals.
Because you can't have it both ways. You cannot be functional as a spoon and a fork at the same time.
I mean, the existence of the spork kind of proves that, yes, you can. You might not be a great fork or a great spoon, but you're adequate at both.
If you are antibiotic resistant, you are losing function in some other area. If you're HIV resistant, you're losing function in some other area. So these beneficial mutations are only beneficial under certain circumstances, and they're very detrimental under others.
Yeah, that's kind of the whole point. That's the very point that Sanford misses. That's why all her talk about genetic entropy is nonsense. Mutations don't have fixed objective fitness effects.
So don't let anybody ever tell you there's...
I am the angel Gabriel.
I haven't found one yet.
Yes, she has. She just listed off some. But the problem is that what she hasn't done is actually figured out what the correct definition of fitness is. This is just like a flat earther saying that while they acknowledge that 9.8 or so meter per second downward acceleration, they reject gravity. Well, that just means you don't know what gravity is at the most basic level. Pam doesn't know what fitness is at the most basic level, and so she doesn't know what fitness effects are.
I've been looking a long time.
You know, if you look for snakes in Arizona, it will take you a long time to find one if your definition of snake is a winged animal with 8 legs and 2 mouths. But on the other hand, if you're looking for scaly reptiles with no walking limbs and a longer torso than tail, you'll find a snake pretty fast.
All right, the last problem is that no matter how much we mutate them, bacteria are still bacteria, fruit flies are still fruit flies, finches are still finches, and peppered moths are still peppered moths.
Again, as required by evolution. What is it with Pam and explaining how evolution works in order to say that it's a problem? It's like explaining Newton's second law of motion in an effort to say that rockets can't work.
We have never seen, and bacteria are mutated at, I did a calculation at one point, the number of generations that we have seen of bacteria that we've been mutating the living daylights out of in the lab, and it's astronomical, and we still have not produced anything. We haven't even made an E. coli that is no longer an E. coli.
That's not entirely accurate.
Actually, one of the defining traits of E. coli is that they cannot metabolize citrate in the presence of oxygen. It's one of the reasons that citrate was used in the medium in the Lenski long-term E. coli experiment. But in that very experiment, a strain of bacteria evolved that could indeed digest citrate in an environment with oxygen. Technically, this means that the E. coli in this experiment no longer meet the traditional definition for the species. But also importantly, where the lines are in species is fundamentally a judgment call and is based on numerous species definitions. Like all taxa, species are fundamentally arbitrary to some degree. Humans like to put things into boxes and label them, and nature doesn't care at all about those boxes. What are real are lineages, and lineages change, and sometimes they can change enough that humans make a new box for them. Sometimes they don't. But whether or not humans decide to set up a new box with a new label is completely immaterial to whether or not evolution has occurred or is occurring in a lineage.
We haven't even done speciation, let alone developed a new kind.
This is so dumb, not even most creationist organizations will agree. In terms of observed instances of speciation, I'll just reach back into the depths of the deep lore of the internet and pull out Talk Origins from 1995. It has a list of observed instances of speciation, and it has been observed in the evening primrose, the Q primrose, the trigopogon, Raphaniobrassica, hemp nettle, brassica species, maidenhair fern, the woodsia fern, maize, the yellow monkey flower, Drosophila polystorum, D. melanogaster, just so much. Houseflies, apple maggot flies, gall flies, flower beetles, lab ratworms, Chlorella vulgaris, and many more in the subsequent 29 years.
Right, and fruit flies, I think the mutation rate has been sped up like 17,000% or something like that over 100 years, because Morgan's fly room was operating in the early 1900s.
And there are dozens of known speciation events in fruit flies in the lab. You can just do it yourself by following the methods of any of dozens of experiments that resulted in genetic isolation between populations of fruit flies taken from a common stock. Even something as simple as giving them different food sources can do it.
Still nothing that isn't still a fruit fly.
Yeah, because that's how evolution works. No matter how much change there is to a fruit fly, it'll be a fruit fly, because that's the lineage it belongs to. You can't make your ancestors not your ancestors. That's logically impossible. Not even the God of Catholicism could do it. And before anyone comments about it, no, that doesn't make the God accepted by Catholics not omnipotent.
It's highly disappointing.
I would imagine so, since if fruit flies ever managed something as absurd as changing their ancestors, that would not only be evidence against evolution, but of the very basics of logic. That kind of thing would upturn more or less everything.
So we're back to genetic entropy.
Oh joy.
Right? And this idea that as mutations accumulate over generations, what we're doing is we're losing order, we're losing function, we're losing specificity, we're getting less and less and less and less perfectly human, basically.
I mean, that is an idea, but it's an idea that violates, like, the basic rules of math. So it's not real. In fact, in some sense, because it's fundamentally contradictory to itself, it's really not even an idea. But that's getting a bit nitpicky.
And as I accumulate these mutations, I'm headed to error catastrophe, which means that the human race will eventually go extinct.
I mean, it doesn't, because the mutation rate isn't nearly high enough to make that an inevitability. Now, the human species will eventually go extinct, but it's extremely unlikely to be because of error catastrophe.
But Christ will come first, so we really don't have to probably worry about that.
Hey, if the parousia is right around the corner, that's great and all, but Christians have been saying that for about 2,000 years, give or take, and it hasn't happened so far. Let's just assume that it's far enough out that we need to worry about the long-term effects of our actions, and not doing things like just not worrying about medical or environmental problems, because we figure that it'll be fixed by the eschatological musings of Christians. Those musings have so far helped no one ever, and have manifestly hurt people. Like the people who sold all their possessions to spread the word about Jesus coming back in 2011, as predicted by Harold Camping, who at least had the good grace to apologize and die afterwards. I'm not saying Jesus isn't coming back, that's not my job. But what I am saying is that it's best to act like that's not happening anytime soon.
Okay, so the case for genetic entropy.
Which is best described as a lie.
Basically, remember, for mutations to be the driving mechanism of evolution, most of the genome has
I've come to bring good news.
to be. It's not, it's mostly useful.
Wrong, but we've already talked about it.
Most of the mutations have to be harmless, but they're not. They're actually only slightly deleterious, but that's still deleterious.
Wrong, but we've already talked about it.
Some mutations have to be good, but even those rare ones that are claimed to be good have a fitness cost to go with them.
Wrong, but we've already talked about it.
And no matter how much we mutate something, we can't make a new kind of organism.
Well, since kind doesn't mean anything, that's not even a real thought, which I think means that even though grammatically it had the form of a sentence, it technically wasn't one.
So it seems like genetic entropy makes a lot more sense as the outcome of mutation than evolution would be.
Are you serious?
And there's a little bit more evidence for this because some recent articles have traced supposed bacterial evolutionary lineages and shown that if those lineages are correct, genomes are actually shrinking over time.
Which isn't a prediction of genetic entropy, so who cares?
Instead of expanding, which is not what you would expect if you were an evolutionary biologist. You expect to be accumulating new information, but it is what you would expect if you were a creationist and you said, well, the fall happened and now we start to have mutations and now we start to lose things.
No. Genome size is selectable because it takes energy to duplicate it. It's not a big fitness difference, but given the insanely large population size of bacteria, that's well outside the range where selection cannot operate. So we should expect bacteria to have relatively high functional fractions of their genome, and to shed genetic material that's not useful.
This is even what you see in domestication, right? Chihuahuas are tiny because they've lost the genes to be big.
What you just said is one of the most insanely idiotic things I have ever heard. At no point in your rambling, incoherent response were you even close to anything that could be considered a rational thought. Everyone in this room is now dumber for having listened to it. I award you no points, and may God have mercy on your soul.
No, because there are no big genes. There are developmental genes, and Chihuahuas have all the same developmental genes as any wolf. The difference is when and how long they are expressed. If they simply deleted those genes, you wouldn't get a small dog, you'd get a dog that is missing bits of anatomy. Which means you probably wouldn't get a dog at all, you'd get a stillbirth.
And they're short-haired because they've lost the genes to be long-haired.
Nope, they have the same genes. In fact, long-haired Chihuahuas are a real thing. The breed rather famously comes in long and short-haired varieties.
They're not short-haired because they've developed some sort of new gene.
Yeah, I guess that's true enough.
So I'll let Dr. Sanford sum up genetic entropy. He says that the genome is actually degenerating. It is bad news for the long-term future of the human race. It's also bad for evolutionary theory. If mutation and selection cannot preserve the information already within the genome, it's difficult to imagine how it could have created all that information in the first place. We cannot rationally speak of genome building when there's a net loss of information every generation, any more than we can rationally speak of wealth building if we're losing 2 cents on every transaction.
Amazing. Every word of what you just said was wrong.
So evolution fails again.
At the risk of repeating myself,
You serious?
Fails to take into account the massive genetic differences between humans. Oh, sorry. That's on a different slide. It fails to establish any room for error in the genome.
wrong, but we've already talked about it.
Fails to offer any true examples of mutations adding new information to the genome.
Wrong, but we've already talked about it.
And it fails to directly demonstrate that the accumulation of mutations leads to new organisms.
Wrong, but we've already talked about it.
And so now there are 2 Star Trek characters doing a facepalm because this is doubly bad.
I wonder if she knows that Star Trek just kind of assumes in the background that evolution works, even though sometimes the writers screw it up.
News? For me?
And that's what I have
What?
left. Yes, go ahead.
What about CRISPR?
CRISPR?
Yes.
Ever God wants.
So
I
method for altering DNA, and it's DNA scissors basically. And they've done some experiments recently in gene editing with in humans actually that were spectacularly failures.
They were spectacularly failures sums up basically every sentence in Pam's talk. The rest of this is just Q&A that's both nearly incomprehensible because of how bad the sound is, and in which Pam makes no new arguments. I guess that means that's it for me and the series. I have no idea if I'll come back to cover more Pam. Given how unoriginal she is, it certainly won't be soon. If you liked the video, please hit like and tell me in the comments. If you didn't, feel free to hit dislike and tell me what the problem was in the comments. Either way, please remember to subscribe and hit that bell icon so you're always notified when I have more content. I'm the Dapper Dinosaur. Hey, before you leave, I just want to take a second to thank my patrons and channel members, especially those pledging $20 or above. Ben Tovend, Phil Ravara, Tapioca Weasel, Whispers, Denny5252, Eleron Teller, Horseflesh, Ian Chen, Kelvin Brostock Van Manen, Landon Knoll, Mabbity Babbity, Monkey They Them, Robert Carpenter, Sphincter of Doom, Vollus, Strawberry Vein, and Ita V. It's because of my channel members and patrons whom you're seeing on screen that this channel can stay afloat. Without you, it would all shut down. If you want to join the team, there's a link to join the channel below this video, and there's a link to join the Patreon in the description. On the Patreon, you can get a 10% discount for pledging annually, and either way, you get early access to virtually all of my scripted videos, often 3 to 5 months before they come out for the general public. Thanks for watching.
I will fool the shepherds. I will know their greatest fear. I will know your greatest fear. Wake up, Joseph. Wake up, wake up, wake up, wake up.